Hello, and welcome to another video in this series as together we go on a journey to learn Prolog. We're currently probably around a third of the way through the course, and we're in the middle of a series of videos exploring recursion. We've done two already. We introduced recursion and then we looked at recursion with lists. Today we're going to take that a little bit further and introduce another quite common pattern called working with an accumulator. The best way to introduce it is actually to see something go wrong and then see how an accumulator is the answer to fixing what went wrong. So today we're going to be trying to solve a very simple, or apparently very simple question, which is how to reverse a list. Or in the language of Prolog, how can we define a property between two lists so that one is the reverse of the other? So the property is true if one list is the reverse of the other. So what do we mean by that? So here's an example list. It's got 1, 2, 3, 4, 5 things in it, and its reverse might be something like E, D, C, B, A. So that's the same list but reversed. So we might have something like a property called reversed. The first list, second list, and then that would be true. So reversed, let's say 1, 2, that's the first list, and the second list 2, 1, that would be true. But if we had reversed 1, 2, 3, and then 3, 1, 2, that would be false because this is not the reverse of this. So that's where we're trying to get to. So the first thing we kind of think about is, okay, in most normal programming languages, there is either a built-in method for reversing a list, quite convenient, it's a thing that we often need to do, or there is a way of working through a list, working your way through, the beginning to the next, or even backwards. And in fact, languages like Prolog go even more sophisticated and allow you to jump in defined steps, so every 2 or every 3 and so on. But in Prolog, there probably are libraries that extend Prolog that allow you to do things like reverse lists and chop them up and do interesting things, and you would typically use them if you were using Prolog for a real world project. But for the purposes of learning about Prolog and learning about the mechanisms inside Prolog, and also to strengthen our own muscles, we're going to build one ourselves. It's a very common thing you'll see in all the textbooks and courses, but it's a useful exercise. So we're going to build it ourselves. So let's think about how we might either test if two lists are the reverse of each other, or build one that's the reverse of another one. How would we do that in Prolog, knowing that Prolog is a very simple language, and we're not going to use external kind of libraries? What do we have at our disposal for working with lists? Well, we know that we can decompose a list by unifying it with this construct, where that becomes the head of the list, so that becomes A, and then the tail is unified with T, so that becomes B, C, D, E. Does that help us? Doesn't immediately seem to be that useful, does it? If this is our only way of working with lists, seems quite primitive, doesn't it? But actually it is still useful. So let's, as with all Prolog problems, The best thing to do is kind of experiment and sketch out on a piece of paper how you might do it. If I have A, B, C, D, E as just a list of things that I want to by hand reverse, what would I do? Well, I might take E first, and then D, and then C, then B, then A. Has that helped us in any way? Not so sure. Let's draw another picture just as we explore the problem. This is to be encouraged. A, B, C, D, E. Now imagine these are kind of little blocks that sometimes children play with. How would we reverse those? What you might do is to move this onto another position, and then move that so it's there, then that so it's on top of that one, and that so it's on top of that one, and then that so it's on top of that one. So it's effectively the same as what we've just done, but it's a little bit more concrete to see what's happening. We've taken several steps to get here, so that suggests that our prologue method might need to take several steps to get to the answer from the starting point. Now remember, prologue is we're not really supposed to think about prologue in a procedural way. We're supposed to think about relations between two things. So what we need to do is think about what's the relation between each of these kind of steps or phases. So actually, let's look at a picture that I drew earlier, which is on the blog as well. So here it is. We have the starting position A, B, C, and then in step 1 we've moved A, the head of this list, onto its own list, and then we move the head again onto the top of the other list, and then we keep going until we've run out of blocks. And that's kind of what you would do if you were a child playing with blocks. How do we express a relationship between each of these inside these phases? What's true here? Well, let's write it out. So here I've drawn a picture just showing the various steps to get to the solution. So we're starting here with our starting list, which is A, B, C, just a shorter one, and we want to end up with a reverse C, B, A, and to get there are various steps to get there. And just to make it clear, what we've got is two lists that we're working with, and one is our starting list and the second will become our solution, but actually starts off as the empty list. And our starting list becomes empty as we take the head off it. So at each step, to go from one to the next, we are taking the head off and putting it onto the head of the other list. But we have to express this in a relationship form, because in prologue we think about relations that are true, not about shifting kind of data around. So what's the relationship here? Well, if this is L1 and L2, list 1 and list 2, the step from one phase to the next is true if, and I'm going to write this not in prologue code but in kind of English, it's true if between L1 and L2, it's true if the head of, so I'm going to write a magic function head of, if the head of list 1 is appended to, or is the head of the second list. That's the second list. And the first list is the tail of list 1 step. So that's true if that relationship is true. So what are we saying here? That sounds quite complicated, doesn't it? What we're saying is that the relationship step, a relation, we just named it step, is true between list 1 and list 2 if the relationship is also true between the tail of list 1, so the tail, and the second list has the head of the first one appended to it. So head of list 1 appended to it. Okay. So that's saying that's true. And is this true of every step? Well, it's true here as well, because between this kind of position and that position, this list, we're starting here now, these two, and we're saying it's true if the tail of that list, which is just C, the tail of list BC is just C, if that's the first one, and the second one is this one, L2, extended by the head of the first one, so I need to clarify that, L2 there. Okay. Yeah, that seems to be a starter. That screen looks a bit messy, so I'm going to write that again, because it needed a bit of thinking just to kind of get there, and sometimes the thinking is a little bit messy, but once you start saying it and writing it down, it becomes clearer. So we could have named that relationship jump or next. We've just called it step. And we're saying it's true between L1 and L2, two lists, if it's true, if it is also true that step relation is true between the tail of L1 and a second list which has the head of list 1 appended to the beginning of list 2. So that relationship is true, and it's true between this phase and that phase, this phase and that phase, this phase and that phase. And that sounds like a recursive relationship because we're defining it in terms of itself. Now remember, with recursive relationships we wanted to check that certain criteria were met. One is, does this reduce the size of the problem by 1? And it does, because this list is one smaller than this one, and this one has grown from this one towards the correct answer. So this is getting smaller, but this is getting larger. So empty A, B, A, B, C, or CBA, getting one step closer towards the solution. So repeated application of this will move from here to here to here until we have an empty list. So we have a stopping function which says that step of empty list is true when the second list is, it just is. So that kind of stops the recursion. So that is a way of expressing in Prolog this idea of, it's almost like the Towers of Hanoi game almost, where we try to construct a list that's the reverse of one that's given. So let's try and code that. Oh, just before we do code that, we just want to illustrate the extending a list. So if we've got a list 1, 2, 3, and I unify that with H, T, we know that H becomes the head of the list and T becomes the tail, and that's a way of chopping off the head, and we've done that in the last video. You might think, well, how can we use this to grow and extend a list? We can do that by saying, if we've got a list, say 1, 1, 2, 3, and we want to extend that, what we have to do is unify it with, say, the list that we want, but it's unified with what we want to extend. So let's say we want to extend it by Apple. So Apple becomes a start. So it's the same as that because it's symmetric. We're saying Apple is the head of the list L, and 1, 2, 3 is the tail of the list L, and that should give us L is Apple 1, 2, 3. So we extended the head of the list. I could have put 0 there to give us 0, 1, 2, 3. So that's working in the doing it in the opposite direction in some sense. Prolog itself, there's not a different kind of instruction for doing this. It's still this construct in a H vertical bar T, but because we're using unification, logically Prolog knows that L is this list with the head 0 and the tail 1, 2, 3. So I hope that makes sense. That can be a bit unfamiliar to some people. So let's have a go at converting our idea into Prolog. So there's the code. Let me just enlarge it a little bit. And we can see the two rules there, continuation rule and the termination rule, which always goes above the other one. So we can see here that the first list is not listed as L1. Well, it could be, but we've just taken the shortcut to break it down into H1 and tail1, H1 and T1 straight away. So if we provide that with 1, 2, 3, H1 will be 1 and T1 will be 2, 3. It's just a common way of, you'll see that with people who write Prolog, do that unification in the head. Just to illustrate that, in case you are confused, if we wrote L1, then we'd have to write L1 equals in the body so that that list is then unified and decomposed into H1 and T1. See what I mean? So we just do that as a shortcut in the head. Great, so that's chopping up the first supplied list, and that's saying this is true if this is true, and in this one it's the tail of the first one, and the second list is the L2 extended from the front by H1, just what we did here. So that's what we've just talked about with our pen and paper sketch. And then we've got the termination rule, because this will, if a repeated application of this rule, will keep chopping off the head of T1 until it's empty, and then we're saying when it's empty, L2 is the reverse. Stop there. That's no need to apply this step relation again. So let's try it. Step, and we want to reverse 1, 2, 3, and tell us what the reverse of that is. So this should be the reverse. So let's run and see what happens. Interesting. So a few things to talk about there. First, Prolog says it's true. Well, that's positive, I suppose. It didn't give us an answer. It didn't tell us what X is. So something's gone wrong. We'll look into that. And remember at the start we said we're going to make a mistake first and then fix it with the idea of accumulators. So we've deliberately done this wrong, in case you're wondering. This is a warning here which doesn't break the program, but it's nice of this particular version of Prolog to say there's an L2 variable which isn't used, and you can see that here. L2 is not used, so there's no point putting it there. It's not going to break the program. It's not kind of illogical. There's no logical kind of incorrectness there, but it's sort of saying, are you sure you haven't made a mistake? If you've created a variable but then you've done nothing with it, that suggests you've gone wrong somewhere. Normally, if you're not interested in the result of a variable, you kind of use an underscore to say, well, whatever's there, but we are interested in it. We do want to know what L2 is when the first list has been reduced to an empty one. So we'll leave that in there for now. So let's try tracing this to see what's going on. Remember tracing from a previous video? It's a way of asking Prolog to tell us what it's been doing. So let's run that. Trace. Run it right through to the end. So you can see it starts off by, we called the step relation, we call the query with 1, 2, 3 as the first parameter, and the second parameter is x. So as we know, Prolog uses its own internal variables with an underscore. It keeps track of these things itself and doesn't tell us what they are. Only at the end does it kind of say, okay, your answer is x equals, or whatever it is, y equals. So that's correct, yep. And the next call to step, because in order for it to prove this is true, it needs to prove this is true. So that's what it calls there, and that's the tail. See, T1, that's the tail of that list, 2, 3. And this one, H1 vertical bar L2, that's the L2 extended by H1, extended by the head of the first list. And we can see that here. We can see number 1 there. And in order to prove this is true, it uses the same relation again. It can't use this one. It might try, but it won't unify because the first one is empty. So we'll try this again, and this time now that list, the first parameter is a list of 1, so it's reducing in size. Can you see 3, 2, 2 and 3, and then 3, while the other one is growing 1, 2, and then 1, 2, 3. So by this call, you can see the first parameter is now an empty list, and the second parameter has 3, 2, 1 appended to it. So that's positive. That looks like we're in the right kind of ballpark. Our debugging is looking encouraging. This is a debugging session. So that's okay. So it looks like we haven't done anything drastically wrong. And because that's now an empty, the first parameter is an empty list, it then matches this first rule, which says it's just true. So if it's just true, that succeeds, and then all the calling goals were succeed all the way back to the start. So it's saying, yep, this is true. So actually, we've not gone too far wrong. What we've done is asked whether it is possible for this list for its head to be chopped off repeatedly until it's empty, and that's all. That's in effect what we've done. And the other thing to notice is that the second parameter, which we wanted to be the reverse of the supplied first parameter, is almost right but not quite. Can you see it's 3, 2, 1, but then there's the a variable still as the tail of that list, because that's what we grew from. We grew from an unknown variable x, and we grew it with 1, then 2, then 3. Shall I draw a picture of that? So we started with an unknown variable, and then we extended it with the first element of the supplied list. So 1, 2, 3 was the supplied first list. So we took the head of that and extended it, and then we did it again, and then we did it again. So the answer grew, but this thing remained unknown. Actually, we should have started with an empty list. And you can see that from our Towers of Hanoi game. Can you see here? We start here with an empty list, not with a variable. So it's an empty list, and then we grow it. So it's almost like we should have started with an empty list. So so let's try providing an empty list as the second parameter to grow from. So let's run that. We're tracing this to see what happens. Okay, that looks a lot more positive. So can you see the first parameter, 1, 2, 3, becomes 2, 3, becomes 3, becomes empty. And the second one starts empty, grows to 1, grows to 2, 1, goes to 3, 2, 1. So that's good. That's much better now. We don't have kind of an unknown variable as the tail of that. And again, if we run that as a normal query, Prolog is just saying, yep, that's true. So what we need to kind of clarify our thinking around is to understand that what we're really asking here is it true that I can keep chopping the head off this list? And that's all we're asking. We're not actually asking to reverse. We're not actually asking us Prolog what the reverse is yet. But in doing this, it has worked out the reverse, so we need a way to pull it out. So let's see how you could do that. Well, at each of these steps, when this rule is applied, the second parameter isn't the reverse. It's in the way to being reversed. It's growing the answer, but it's not quite there. It's only when the first rule is matched, because the first parameter is empty, only then is the second parameter the answer we want, the fully reversed list. So we need to find a way of getting that out. So how could we do that? Well, one way is that we create another parameter that we keep passing. So we do nothing with it. Can you see here, x and x? It's there, but it's not really, nothing really happens. It's just passed right through. And then when we finally get through, so we start off by calling x there, and here we don't know what it is. So we don't know what it is there, we don't know what it is here. And then to resolve this is called again, and x is passed through again and again, and we don't know what it is until the first starting parameter is an empty list, and this one is the answer we want. And then we can unify it. We can say that is actually L2. Do you see what I mean? Let's write that out to see what happens. So we start off with step 1, 2, 3 as a list. We create a parameter, a variable x, and we start the third one as an empty list. That's true if step 2, 3 x, and this is 1, is true. And that's true if step 3 x 2, 1 is true, which is true if, so I'm just stepping through in the same way that Prolog would, step empty x 2, 1 or 3, 2, 1. And this one, we don't need to call that continuation rule again. We can call the termination step because this is now empty. And that termination step is step empty L2, L2. Do is just true, which means this unifies with this, and this unifies with this, and they're both the same name. So X is finally, so here we don't know what it is, here we don't know what it is, here we don't know what it is, and now we do, because it's L2. It's been unified by the termination rule. So unification, I know we've talked about it before, but it's really powerful. You know, this is a use of unification in the head of that termination rule. So when we get to the termination rule, the second and third parameters are unified, and X is finally given a value, which is this, the fully reversed list. Let's see if that works. Right, let's run. Yep, magic. See, it worked. So now we've got X is 321. So in a way, what we've done is we provided a parameter, a variable X, which only gets a value when all the steps are done and it reaches the termination step, and only then is it given a value. It can't be given a value before then because there isn't enough information to know what it is. It's only at the very last step that we know what X is. We could have used XX or even YY. It doesn't really matter. All it's saying is the second and third parameters are the same as a fact. It's a basic fact, so that would still work here. There you go. So let's I'm just going to do that for clarity. So so what about accumulators? What is an accumulator? So what we've done here is we've grown. By the way, you can read this on the blog in your own time if you needed to kind of read more carefully written words about this topic. So an accumulator is just a thing, a variable, or a structure which grows to the right answer as a number of steps are kind of applied. So this accumulator starts at 0 and grows and grows and grows until it gets to the right answer, and then it's pulled out. So that's a word used to describe the function of that second parameter here, and it became our third parameter. So that's just what an accumulator is. So the accumulator here is 0, and it's an empty list, and then it grows until it's the fully reversed of the first list. Right, so that's almost nice. You would expect, when we wrote this at the start, we wanted something like reversed 1, 2, 3 X. We wanted something like that, not what we've got here, which is 1, 2, 3 parameters. We've got an arity of 3, but we don't need to know about that third one. That's a kind of a detail of the method of the algorithm. So what can we do? Because we don't want to be having to write that every time we want to use a reversed kind of query. Well, we can wrap it, and what that means is we can write reversed x comma y. That's true if step x y comma empty. So this is how you'd call the step kind of relation. But this is kind of hiding the fact that we create an empty accumulator. So we've wrapped it with a simpler kind of property. So this is true if this is true, and here we don't need to mention the accumulator because it's just a detail of the method. So this is called wrapping. We wrapped this one with this one. We wrapped this relation, this property with this property. So let's see if that works. Yep, it does. So that's quite nice. Lovely. So A, B, C. That works. Oops, A, B, C, not A, C, C. Brilliant. So we'll stop there and just kind of remind ourselves what we've learnt. We've learnt about lists before, and we've learnt about decomposing them into heads and tails. Here we've used the heads and tails method to actually construct and append and grow a list from the front. And we initially thought maybe that wasn't possible, but through unification we can do that. We've deliberately did an incorrect algorithm, an incorrect process for reversing a list, but then we used tracing, we practiced tracing to see what was going on, try and fix it. And our fix was to use an accumulator and this method of passing a variable through a recursive continuation rule until the termination rule, where it's unified with the actual answer, which then pops out. Fantastic. So I'll stop there. That's a good achievement. Bye.